We always talk about the cloud like it's, this ethereal, weightless thing.
Right.
Like
Yeah.
you write some code, you push it, and it supposedly just scales with like zero physical friction.
Yeah, that's the grand illusion of the internet.
Exactly. But if you look at the capital expenditure of the tech giants right now, I mean, that illusion is just completely shattering. We're watching the industry abruptly stop treating AI as, well, just a neat software tool.
Right. It's totally shifting.
Yeah, and they're starting to treat it as a heavy industrial manufacturing process. Like they're literally building what they call the AI factory. And, factories require raw materials, heavy machinery, and just mind-boggling amounts of power. So welcome to the deep dive.
It really is a brutal collision between digital ambition and physical physics. I mean, for a long time, software engineers didn't really have to worry about thermodynamics.
Right.
But now, manufacturing intelligence is forcing this massive physical reality check that, well, it's altering the economics of the entire tech sector.
So our mission today is to decode that exact shift for you. We are synthesizing a really heavy-hitting stack of sources to figure out, where all this is going.
Yeah, it's a great lineup today.
We've got a CTO's guide to Nvidia's new Blackwell architecture, deep equity research from Safra unpacking the semiconductor industry's economic moats.
Which is fascinating, by the way.
Super fascinating. Plus, some really cutting-edge academic papers looking at agentic ROI and a compounding system called King Claw, and, industry analyses on the sheer economics of modern data centers. So, okay, let's unpack this.
Let's do it.
Why this sudden shift to the factory model, and how does treating AI tokens as physical capital goods fundamentally change how every business operates?
Well, to understand the factory, you really have to look at the engine first. Because for the last few years, the industry standard has basically been Nvidia's Hopper architecture.
Like the H100 chips, right?
Exactly, the H100. And that was the hardware that powered the massive pre-training runs for, like, all the models you use today.
Yeah.
But we are crossing a major threshold right now with the new Blackwell platform, specifically the B200.
Yeah.
It is a completely different approach to silicon.
Yeah, reading through the CTO's guide, I mean, the architectural shift is just wild. Because for decades, the goal was always just to etch, smaller and smaller transistors onto a single monolithic die of silicon.
Right, Moore's law.
Exactly. But Blackwell doesn't do that. It actually uses this chiplet design where they take two massive, like 800 square millimeter dies and just stitch them together.
Using TSMC's co-cell packaging, yeah.
Right. And it effectively doubles the physical footprint of the brain.
And that's because we essentially hit the reticle limit.
The reticle limit.
Yeah. So there is a hard physical cap on how large a lithography machine can actually print a flawless piece of silicon. You just can't make the canvas bigger anymore.
Oh, wow. Okay, so you physically can't just print a bigger chip.
Right. So to keep scaling performance, you have to print two separate massive canvases and then bridge them. But that bridge has to be so incredibly dense, with such high bandwidth, that the software actually thinks it's still talking to a single unified chip.
Okay, that makes sense.
Yeah, and co-SL allows those two dies to communicate at, get this, 10 terabytes per second.
10 terabytes per second. That's absurd. But it solves the physical manufacturing limit.
It does.
But alongside that, they also completely changed the math with FP4 precision, right? Like a 4-bit floating point format.
Yeah, and this is where we see the software and the hardware really co-evolving. Because historically, you wanted high precision for computing things 16-bit or 32-bit math.
Like if you're calculating a bank balance or a rocket trajectory.
Exactly. You need perfect decimals for that.
Yep.
But large language models are probabilistic. They don't actually need perfect precision to guess the next word.
They just need like a general direction.
Right. General directionality.
So by dropping down to 4-bit precision, you are radically shrinking the memory footprint of every single parameter. And the model can make its probabilistic guesses much faster because it's just moving way less data around the chip.
Spot on. It creates this massive leap in inference efficiency without, a noticeable drop in output quality. But, and here is the inescapable physical trade-off.
Uh-oh.
By stitching two massive dies together and running them at these blistering speeds, you run headfirst into a thermal wall.
Right, the heat.
A single Blackwell GPU consumes up to 1 kilowatt of power.
1 kilowatt.
Yeah.
Which, just for context, is a 40% jump from Hopper's 700 watts.
Yeah.
And this is where that software illusion we talked about really breaks down for me. Upgrading to Blackwell isn't like, just buying a faster laptop. It's like buying a state-of-the-art high-speed bullet train, only to realize your city's electrical grid and physical tracks just cannot support it.
That's a great analogy.
Right. I mean, the chip is essentially useless without retrofitting the entire environment around it. So doesn't this massive power draw just ruin the basic economics of the data center?
Well, it forces a mandatory structural teardown. I mean,
Yeah.
you physically cannot cool a dense rack of 1 kilowatt chips with forced air anymore.
Just blowing fans on them won't work.
No. The fans would have to spin at jet engine speeds.
Yeah.
The acoustics alone would literally destroy the hard drives in the same room.
Oh, wow. Just from the sound wave.
Exactly. So the total cost of ownership, the TCO, completely shifts. Buying Blackwell mandates a facility-wide transition to direct liquid cooling, or DLC.
You're installing, like, massive plumbing manifolds.
Yeah, plumbing, you need reinforced floors just to handle the weight of all that water.
Yeah.
You need entirely new power distribution units just to handle the raw amperage.
So the silicon is really just a down payment on the plumbing.
It really is.
Yeah.
Which means your hardware choice is now an infrastructure destiny. If a company's data center cannot handle a liquid cooling retrofit, maybe they, don't have the floor load capacity or they don't have water access, they can't just buy Blackwell.
They're locked out.
Right. They're forced to stick with older architectures or look at value-focused alternatives. So suddenly, Intel's Gaudi 3 or AMD's MI300X become very compelling for companies that are prioritizing a lower TCO over, absolute peak performance.
Okay, so if we are spending billions on plumbing and structural reinforcements, the output better be worth it. And according to the software equity research, that output is the token.
Yes, the token.
The entire architectural goal of these mega facilities is to optimize the manufacturing of tokens. They call it tokenomics.
Tokenomics is basically the new unit of industrial value. Think about it. You have a fixed amount of power entering your facility. Your profit margin is dictated by your cost per watt to generate a token. So if Blackwell lets you generate 10 times the tokens for that same megawatt of power, your factory is exponentially more efficient. And this optimization is critical because the nature of compute demand is rapidly shifting right now.
Right, because for a long time, the massive power draw was all about pre-training, right? Like spending months just crunching the entire internet to build a foundation model.
Exactly. But now we are seeing the bottleneck shift toward inference. Specifically with these new models like OpenAI's O1, we're moving heavily into test-time compute.
Test-time compute, okay, and that changes the location and scale of the power demand.
It does. Because test-time scaling means that instead of just, spitting out a fast, intuitive answer, the model actually generates thousands of invisible thinking tokens.
Oh, so it's reasoning in the background.
Right. It reasons through a complex problem, it tests hypotheses, and it discards bad paths before it ever actually shows you the final answer.
So it's essentially trading compute time during inference for higher accuracy on really hard problems. And then you add in agentic scaling, where an autonomous system is running, like multi-step workflows, checking databases, verifying its own code, and you are suddenly burning through millions of tokens for a single user request.
Millions. For one prompt.
But, okay, I have a really hard time buying this infinite growth model long term.
How so?
Well, if Blackwell makes token generation exponentially cheaper, and then the next generation makes it cheaper still, eventually the cost per token has to approach zero, right? At that point, why are we building more billion-dollar factories if the market is saturated and the product is virtually free?
That is a very common assumption. But it ignores the fundamental behavior of resource economics. What you're describing is actually a perfect setup for the Jevons paradox.
Wait, is that the 19th century coal theory?
Yes, exactly. In 1865, this guy, William Stanley Jevons, watched steam engines become radically more efficient. And common sense suggested that because the engines were more efficient, aggregate coal consumption would drop.
Right, because you need less coal to do the same work.
Exactly. But the exact opposite happened. Because steam power became cheaper and more reliable, it suddenly became economically viable to use steam engines for entirely new industries. Railways, shipping, massive factories.
Oh, I see.
Yeah, aggregate coal consumption absolutely skyrocketed.
So cheaper tokens don't mean we just spend less money doing the exact same AI tasks we do today.
No, not at all. Cheaper tokens mean we start deploying AI into enterprise applications that were previously just, too expensive or too complex to even consider.
Wow.
Lowering the cost per token doesn't cannibalize your compute demand at all. It radically expands your total addressable market.
Which brings up a critical competitive dynamic here. If token generation is just an industrial process, eventually hardware becomes a commodity, right? Like AMD or Intel could just build a cheaper, cooler factory engine. So why does Nvidia maintain such a dominant moat if this is all just about, moving math around a silicon board?
Well, because the liquid-cooled silicon is really just the physical manifestation of a two-decade-long software trap.
A software trap.
Yeah, NVIDIA's real moat is CUDA.
Yeah.
That's the programming ecosystem they released way back in 2006. It's the translation layer that lets developers actually talk to the GPU to accelerate general-purpose computing.
And the key detail in that CTO guide is backward compatibility.
Huge detail.
Right, because there are over 7 million developers building on CUDA. Code written for older generations of chips just runs seamlessly on Blackwell.
Perfectly. And competitors like AMD, they have incredible hardware, but they don't have a 20-year-old entrenched software ecosystem.
Right. Asking the industry to abandon CUDA just to save on hardware costs is like asking the entire global financial system to rewrite all their legacy mainframes over a weekend.
Yes.
It's an insurmountable vendor lock-in.
It really is.
Okay, here's where it gets really interesting. So NVIDIA controls the factory floor, but having a factory that spits out cheap tokens is totally useless if enterprises can't actually deploy them to solve real business problems.
Which is harder than it sounds.
Way harder. When you try to take this incredible compute power and just drop it into a standard Fortune 500 company, you slam right into what the SiliconANGLE analysis calls the deterministic myth.
Ah, the deterministic myth. It is the great delusion of enterprise IT.
Exactly. Companies love to pretend that their operations are perfectly logical machines. Like they look at their ERP systems and their CRM databases and they think, yes, this is ground truth.
Right. Everything is perfectly categorized.
Yeah, but anyone who actually works in an office knows the reality is an absolute application jungle.
The messy middle.
Yes. The messy middle. The systems just don't talk to each other. They have wildly different definitions of the exact same data. I mean, think about a supply chain manager asking, why is our shipping delayed?
Right.
The deterministic ERP system says the status is just in transit. But over in the CRM, there's a logged email from a vendor mentioning a local port strike.
And those deterministic systems cannot reconcile that conflict.
No. The only thing that bridges that gap today is human glue. Employees just using their own tribal knowledge to figure out what's actually happening.
And this is exactly where the AI factory finds its highest value application. Because we are shifting from a paradigm of what happened, which is, all a deterministic dashboard can tell you to what should we do now?
Right. Action.
But for an AI to answer that, it can't just be a chatbot sitting in a little browser tab. It has to become a semantic operating layer.
It has to sit directly inside that messy middle.
It does. It has to coordinate probabilistic agents that can actually look at the ERP, read the CRM emails, understand the context of the port strike, and then proactively propose a new routing schedule.
Wow.
But to do that effectively, the AI needs a memory layer. It needs semantic retrieval and corporate policies baked directly into its architecture, so it actually knows the rules and the history of the company.
But if that semantic operating layer is the holy grail, why is it currently so incredibly difficult to deploy these autonomous agents?
Which brings us to that research on agentic ROI by Liu and colleagues.
Yes.
This fundamentally reshaped how I view the limitations of current models.
That agentic ROI framework is so crucial because it strips away all the marketing hype and just looks at the raw economics of agent deployment.
Right.
Liu's research exposed this fascinating inverse relationship. Basically, the domains where users most desperately want an autonomous agent-like acting as a broad personal assistant or, handling complex e-commerce shopping, those are actually the domains that yield the lowest return on investment.
So if I'm understanding the paper correctly, the problem isn't that the AI lacks the raw intelligence. It's more like a context-switching tax.
That's a really great way to frame it. The research points out the difference between topic concentration and topic diffusion.
Okay, unpack that.
Sure. So if you ask an agent to help you code or to assist in scientific research, the topic is highly concentrated. It operates within the same code base or a narrow set of technical concepts. So the context it loads into its memory is tight, and it's highly reusable across multiple queries.
Right, it doesn't have to relearn what it's looking at every 5 seconds. Exactly. Yeah. But a personal assistant agent is dealing with massive topic diffusion. You ask it to buy running shoes, then negotiate a flight change, then, I don't know, summarize a legal contract.
It's like forcing an employee to sprint to a completely different building for every single task.
Yes, it has to start completely from scratch, fetching entirely new context, and burning through thousands of tokens every single time with zero reusable value for the very next task.
The token cost is astronomical, and the memory is completely transient,
Right.
which perfectly sets up the solution proposed by that King Claw system we looked at.
Based on Andrej Karpathy's LLM wiki paradigm.
Yes, and this paper just completely blew my mind. They ran a direct economic experiment to compare how different AI systems handle complex, multi-step questions, measuring the raw token cost.
And the baseline comparison is really revealing. First, they looked at standard chunk rag, retrieval augmented generation. You ask a question, the system searches a database, grabs a small chunk of relevant text, and generates an answer. Over a series of 4 questions, that method cost about 13.6K tokens.
But the critical flaw there is that as soon as the answer is generated, the system just throws the context away. It's completely temporary.
Exactly. Then they tested the long context method, where you just brute force feed the entire massive document to the AI every single time you ask a question.
Which ensures high accuracy, but it costs a staggering 305K tokens for those exact same 4 questions.
Yep. And again, it forgets everything the moment the session ends.
Then you look at the King Claw compounding method. Over those same 4 questions, it used 47K tokens.
Right, so it sits right in the middle.
Yeah, it's more expensive upfront than basic RAG, but it's way cheaper than brute forcing the long context. And this is the kicker, the raw token count isn't actually what matters here. It's the structural permanence of what those tokens actually built.
Because King Claw isn't just generating text, it is physically constructing a knowledge base.
Yep.
It operates on 3 distinct mechanisms. First, it ingests the raw documents once and builds a structured, centralized wiki.
Okay.
Second, it utilizes an auto-feedback loop. So when a user asks a complex question and the AI generates a high-value synthesized answer, it doesn't just throw it away. It automatically writes that insight back into the wiki as a brand new permanent page.
It remembers its own deductions.
Yes. And the third mechanism is the one that really changes the game for the enterprise Missy Middle. Auto write back of search results.
This part is wild.
It is. If you ask the agent a question and it doesn't know the answer, it goes out and searches external sources. But instead of just handing you the answer and resetting, it permanently updates the wiki with those external findings.
The knowledge base is self-evolving.
Exactly.
So upgrading to this compounding method is essentially a shift in how we pay for intelligence. Like traditional RAG is like renting an apartment. You pay your 13.6K tokens in rent. You get a place to stay for the duration of the query, but when you close the tab, you walk away with absolutely nothing. The King Claw method is like paying a mortgage. You pay a bit more upfront with 47K tokens, but you aren't just consuming compute. You are building permanent equity in the system.
That analogy cuts straight to the most important theoretical breakthrough in the paper, because the authors argue that we need to fundamentally reclassify how we view tokens.
Right.
They are no longer transient consumables. They are capital goods.
Oh, wow. Reclassifying a digital token as a capital good sounds like, a CFO's ultimate fantasy. But what does that actually mean for the architecture of a tech company?
It means the entire accounting model for AI just flips. The paper actually draws a very deliberate parallel to SFAS 86, which was a major accounting rule change back in 1985.
Oh, I've heard of this.
Yeah, before that, software development was treated purely as a sunk operating expense. No different than like paying the electric bill or buying office supplies.
Yeah.
But SFAS 86 recognized that software code actually provides future economic benefit.
Yeah.
So it was reclassified as a capitalized asset.
Which changed the valuation of the entire software industry overnight.
It did. And the King Claw paper argues the exact same transition is happening right now with AI tokens. The tokens you spend writing that persistent wiki page aren't an operating expense.
Right, because the next time a supply chain manager asks a related question about, say, that port strike, the AI doesn't have to search the web or process the raw CRM data all over again.
Exactly. It just reads the highly concentrated wiki page it already built.
So the query becomes incredibly fast, and the token cost drops to almost zero. You paid for the knowledge creation once, and now it just pays compounding dividends.
Yes.
You are turning transient compute into automated corporate infrastructure.
Knowledge is finally earning compound interest.
Wow. So bring this all together, whether you are, prepping for a boardroom meeting, trying to justify a massive data center budget, or you are just insanely curious about how the tech industry is reorganizing itself right now, the through line is undeniable.
It really is.
Intelligence is no longer just a weightless software trick. It is a manufactured good. The physical infrastructure of the internet is being ripped down and replaced by liquid-cooled mega factories powered by incredibly dense, massive silicon engines.
And on the software side, the paradigm is shifting from renting a model's context for a quick chat to building capitalized, permanent AI knowledge bases that actually gain value over time. And if we follow that logic to its ultimate conclusion, it leaves us with a rather profound implication for the future of any organization.
What's that?
Well, if an enterprise's AI agents are constantly learning, constantly pulling in outside context to resolve that messy middle we talked about, and constantly writing their findings back to a centralized compounding wiki, they are turning transient interactions into permanent capital assets.
Right.
Which forces you to ask, does a company's greatest operational asset eventually shift away from the brains and tribal knowledge of its human employees and directly into the self-evolving memory of its AI factory?
Wow, that is a staggering thought to leave on. I mean, if the AI becomes the ultimate keeper of the company's experience, the humans really just become the temporary operators of the machinery. Who truly owns the experience of a company when the AI is the one remembering it all?
It's definitely something to think about.
Something to definitely mull over as you watch these massive liquid-cooled data centers rising up around the world. Thanks for joining us to decode the AI factory today. Keep questioning, keep exploring, and we'll catch you on the next deep dive.